Hi everyone. Today I want to discuss about my code regarding a title called a comparative study on solar energy forecasting using machine learning models. Here in this, first I've imported some necessary libraries, which is pandas, numpy, for creating the basic libraries, and I've used matplotlib and seaborn, which is to visualize the data, and I've imported warnings to ignore clean output. In this I've done this code in Google.colab to upload my file dataset. And next step is data collection and pre-processing EDA. In this, I've loaded the datasets into the pandas and to display first few rows for the dataset content. And in this, again, to display the number of rows and columns in this data frame, I had 8,760 rows and 8 columns. To display this information about the data frame, I've used .info. And to convert a date column into date time objects into some specified time format for time series analysis. Again, I've displayed the first few rows to verify the date format conversion. I've used dot head to create to set the data column as the date frames index to facilitate the time series operations. I've displayed again the first few rows to confirm the date column as now the index. Again, I've used dot head to print my first few rows, and here you can see that my parameters, which is wind speed, sunshine, air pressure, radiation, air temperature, relative air humidity, system production. Again, to checking the missing values in each column, to understand the data completeness, I've used .isna.sum, and to calculate the correlation matrix for all columns in the data frame, I've generated a heat map to visualize the correlation matrix, including correlation values. I've used sns.heatmap. In this, you can see that the values are centered +1. A value which is +1, that means it is a strong positive correlation. A value which is -1, that means it is a strong negative correlation. A value which is 0, which is a 0, which has no relation. And in this, I have observed some correlations between key features. In this, +0.7, which is system production and radiation, has a positive correlation, and radiation and sunshine is like next to the system production radiation, and radiation and relative air is -0.60, that which is a negative correlation. To address the multiclonality, I've used some techniques which are such as variance inflation factor VIF to quantify and mitigate any multiclonality issues. I've used some necessary libraries for plotting the graphs. I've used Matplotlib and Seaborn to visualize my histograms, bar plots. Uh, yeah, and in this, I got some plots. Here you can see that most values were like in the middle. That means at that time the sun were more stronger. So again, for setting the plotting style, I've created an axis object for the plots, and to adjust the layout to prevent clipping of the labels. Here you can see that on x-axis it has years and months, and the y-axis it's a system production. So it's my like the data set, the how many object data types were there. So in this, at some months it is like if you see that in the starting month it is like very low, but that means the sun is very low. And if you see in the middle, comparing from 27th in March to 27th in May, that means the sun is more. And again from that, there is no sun, that means there is no sun. And again, I've displayed first few rows to show the newly added date component columns. That means uh, uh, to display first few rows for resulting the daily aggregated data frame. Again, I've generated a line plot for showing the daily average system production over time by using sns.lineplot. And I've imported the necessary plotly libraries for creating some interactive plots, which is plotly.graphObjects and plotly.subplots. And here you can see that there it generates some plots, which is system production aggregation for daily, weekly, monthly, where most values were centered around. That means at that time the sun were more. And I've done outer layer analysis for each my parameters. So again, and after I've done calculator for the quartiles, I've used first quartile and third quartile to print some IQR values, where you can see that. And Again, I've done for VF for checking the multi-collinearity. I've imported some necessary libraries like stats model dot and stat model that starts outliers. Here, we are the three types: low VF, moderate VF, and high VF. Low VF is less than two. Moderate VF is between two to three, and high VF is similar to five. Where radiation is similar to five, that means it is a more. And adding the features again, I have displayed some few rows to add my newly cyclic features. So after this, I've displayed a few rows to confirm my column reordering. Again, I've generated a heat map to visualize the updated correlation matrix with all the cyclic features. Again, you can see that radiation and system production has a strong positive correlation, and relative air humidity is a 0 minus 55, which is strong negative correlation. I've done model building using these machine learning models, which are linear regression, sphere, random forest, decision tree regression, gradient booster regression, LSTM. I've done this thing two sets like training and testing with 80:20 ratio. Here I've displayed the first few rows for the new data frame with the default integer index. I've displayed the few features in linear regression by using the evaluation metrics R square, RMSE, MAE map. I've got the values, and next I've performed SVR. Again, I've trained the data, and again I got the values. And next I've done the random forest regression. Again, I got the values by using these evaluation metrics. And then I've used gradient boosting. Same, I've trained the data and I've tested the data, and by using these evaluation metrics I got the values. And next, XGBoost regression, by using the import libraries XGBoost. By using these evaluation scores, I used evaluation metrics. So then after that, I've tuned the hyperparameters, which is like by containing all the predictions for each trained models. So then I got the values, and best performance model, performing models without the time dimension is random forest, which is 0.99, because it demonstrates excellent predictive capability rather than gradient boosting and XG boosting. Both other models also like has a strong container for the results. And then I've tuned for gradient boost regression. Again, I've used this evaluation score for the best models. So here in this RMS scores more, and then I've tuned up a hyperparameter for XGBoost regression. Again, I got this best performing model was random forest drug regression because it scored highest among all the models. Conclusion: random forest regression would be recommended choice for this problem due to its superior predictive performance, because radiation is as high. It's like more than plus 0.79. Thank you.